Morning, sir.
This is another major topic, subtopic, oxides and oxyacids of nitrogen, phosphorus, sulfur, and chlorine. So let us move to one by one. Oxides of nitrogen into NO, N2O3, NO2, N2O5. Oxides of phosphorus, P2O3, nothing but P4O6. Next P2O5, nothing but P4O10. We have some other oxides also, mainly those two, trioxide, pentoxide. In addition to trioxide and pentoxide, phosphorus form some different oxides also. One is P4O7, P4O8, P4O9. But major both first two. Next, oxides of sulfur, mainly these two, SO2, SO3. Next, oxides of chlorine, Cl2O, ClO2, Cl2O6, Cl2O7. These are the first oxides: nitrogen, phosphorus, sulfur, and chlorine. Now let us move to a few points about these oxides. Important points related to oxides of these four elements. Next. So N2O, NO, N2O3, NO2, and N2O5. Nitrous oxide, nitric oxide, dinitrogen trioxide, nitrogen dioxide, dinitrogen pentoxide. Laughing gas. This is called as nitrogen sesquioxide. Now, sesquioxide means 2:3 ratio oxides. All 2:3 ratio oxides are called sesquioxides. Suppose B2O3, Al2O3, Cr2O3, Mn2O3, such type of 2:3 oxides are called sesquioxides. Plus 1, plus 2, plus 3, plus 4, and plus 5. Oxidation states are oxidation state of nitrogen in different oxides. So as the oxidation state increases, acidic nature of oxides also increases. So out of these 5 oxides, Nana, N2O and NO are neutral oxides. N2O3, NO2 and N2O5. These three are acidic oxides. In these acidic oxides, next point, N2O3 less than NO2 less than N2O5. Acidic nature of oxides. Next point. Generally, Nana, oxides plus H2O, we call them as oxyacids or oxoacids. Oxyacids or oxoacids. Suppose we have 3 acidic oxides here, N2O3, NO2 and N2O5. So plus H2O, plus H2O, plus H2O. Then we are getting oxyacids. Nitrogen, we have 2 important acids. One is HNO2, another one is HNO3. Nitrous acid, nitric acid. So here, problem arises. Which oxide form dash oxoacids? Three oxides we have. So out of these 3, which one form nitrous acid? Which one form nitric acid? One method I am giving here. Generally, in oxides and oxyacids, most of the cases you have to maintain same oxidation state. Same oxidation state means, if suppose we have N2O3, nitrogen is in +3 oxidation state. So in these 2 acids of nitrogen, here we have +3, here we have +5. Therefore N2O3, by dissolving in water, it gives HNO2, only HNO2. If you take N2O5, it is in +5 oxidation state. Then N2O5 with water gives HNO3, only nitric acid. But what about NO2, Nana? NO2 having +4 oxidation state. In such cases, we are getting both acids because +3, +5 intermediate, no +4. That's why it gives both HNO2 and HNO3. Based on this, we call it as N2O3 is called as simple anhydride of HNO2. Next, N2O5 is also considered as simple anhydride of HNO3. But what about NO2, Nana? NO2 is not simple anhydride because NO2 with water it is giving 2 acids. That's why NO2 is called as mixed anhydride, not simple anhydride. Please highlight this word, mixed anhydride of HNO2 and HNO3. And that too, this reaction, a second reaction, the disproportionation reaction. So out of oxides of nitrogen, dash undergoes disproportionation reaction with water means that is NO2. So this word is important now. Mixed anhydride of HNO2 and HNO3 is NO2, whereas N2O3 and N2O5 are simple anhydrates of nitrous acid and nitric acid respectively. So HNO2 is nitrous acid, HNO3 is nitric acid. So since N2O3 with H2O gives only one acid, N2O5 with water gives only one acid, whereas NO2 with water gives two acids. Based on this, next point. Now N2O3, now I'm reacting with NaOH. Similarly, NO2 with NaOH. Next, N2O5 plus NaOH. My acid-base reaction, Nana. Acidic oxide, NaOH base, salt plus water comes out. So in first case, N2O3 case, what type of salts comes out? Salt corresponding to nitrous acid. Salt corresponding to nitrous acid. N2O5 gives salt corresponding to HNO3. Whereas NO2 gives salts corresponding to both nitrous as well as nitric acid. And N2O3 with NaOH gives only one type of salt, that is HNO2 salt, Nana. HNO2 salt means NaNO2 salt plus H2O. N2O5 with NaOH gives HNO3 salt. HNO3 salt means NaNO3. Only NaNO3. Whereas NO2 with NaOH, two types of salts comes out. Two acids, two salts. So HNO2 salt, NaNO2, HNO3 salt, NaNO3 plus H2O. Once again, please highlight second reaction. So plus 4, plus 3 and plus 5. Disproportionation reaction. That means among oxides of nitrogen, NO2 undergoes disproportionation reaction with water as well as with alkali. Alkali means strong bases. With NaOH, two types of salts. With NaOH, only one type of salt. With NaOH, only one type of salt comes out. N2O. It is a linear molecule. And this N2O two nitrogens, one oxygen. 2 into 5, 10 electrons, 1 into 6, 6 electrons. So total 16 electrons. 16 electrons means we can write 8 pairs of electrons. So no unpaired electron, no odd electron. All are pairs. That's what the diamagnetic species, N2O. So totally 8 pairs we need. So I propose two structures for N2O. Out of these two, which one is most stable structure or more contribution for the original structure of N2O, resonating structures of N2O? Out of these two, which one contributes more? Structure 1 na or structure 2 na? Decided by formal charge. Formal charge. Let us write here numbering, Nana. 1, 2, and 3. So let us take structure 1 I am taking. In structure 1, so here formal charge is equal to number of valence electrons in free state 5 minus half of number of shared electrons 6 minus number of unshared electrons 2. Shared electrons, unshared electrons, and 5 is number of valence electrons in uncombined state. Uncombined state means in free state. So here we are getting how much, Nana? 0 formal charge. Coming to middle nitrogen, formal charge is equal to 5 valence electrons in uncombined state minus half of shared electrons 8, 3 left side, 1 bond right side. Unshared electrons is 0. So this is plus 1 formal charge. For oxygen, formal charge is equal to 6 in free state, in uncombined state, minus half of shared electrons 2 and unshared electrons 6 electrons, lone pairs of electrons. Then we are getting here minus 1 formal charge. So in first structure, 0, plus 1 and minus 1 formal charge. Now let us move to second structure. In second structure, N double bond N double bond O, 4 unshared electrons, 4 unshared electrons. But don't put pair near central nitrogen, Nana, because nitrogen second period element, it can accommodate maximum 8 electrons only. So already 8 electrons are over. Now coming to this second structure of nitrous acid, here formal charge is equal to 5 minus half of 4 minus 4 unshared electrons. That is minus 1. Now middle nitrogen, central nitrogen, formal charge is equal to 5 minus half of 8 electrons, no unshared electrons. That is equal to plus 1. For oxygen atom, terminal oxygen, formal charge is equal to 6 minus half of shared electrons 4, unshared electrons 4. So this is equal to 0. So for second structure, here we have plus 1, here we have minus 1, here we have 0 of formal charge. Now based on these two formal charges, first structure is contributes more contribution first structure, because in second structure oxygen is carrying 0 formal charge, Nana. In first structure oxygen is carrying negative formal charge. Since among nitrogen and oxygen, oxygen is more electronegative, it should carry negative charge. But in second structure, even though nitrogen is less electronegative, it is carrying negative charge, negative formal charge. That's why second one is less contributed structure. First one is more contributed structure. So N2O means generally we are writing first structure, N triple bond, N single bond O.
Sir,
Tell me now.
second structure లో టెర్మినల్ నైట్రోజన్ కి -1 కదా సార్.
-1 Nana. Right. Middle one ki plus 1, right. This is -1, right, Nana. Then only totals becomes 0. Sum of formal charge should be 0 for neutral molecule, right now. That's why for nitrous acid, generally we are representing like this, resonance hybrid, Nana. N bond O. But not single bond. Generally we are representing like this, nitrous oxide. this is 113 picometers. This is 119 picometers. Bond length in nitrous oxide. Next, NO. So N 5 valence electrons, oxygen 6 valent electrons. So total 11 electrons. 11 electrons means how many pairs nana? 5 pairs plus one extra electron is there. That's why this type of molecules are called odd electron molecules. 5 pairs plus one electron, odd electron molecule. And paramagnetic gas, odd electron molecule, paramagnetic gas, and this NO is colorless gas. And this NO, nitrogen, oxygen. Okay, so total 11 electrons we have to accommodate. 2 electrons, 2 electrons, two resonating structures, odd electron near oxygen, odd electron near nitrogen. N double bond O. N double bond O. But that odd electron, bond means 2 electrons, no? But now this bond I am writing with 3 electrons. Just resonating structure, Nana. That odd electron involved in bonding also. We have in diborane 3-centered 2 electron bond. 3 atoms with 2 electrons. But here 2 atoms with 3 electrons. 2-centered 3 electron bond. With this NO, 3 electron bond also present in one of the resonating structure. 3 electron bond. So generally we are representing like this N bond O for nitric oxide. 115 picometers bond length. Now because this is odd electron molecule, paramagnetic gas in the bracket with one unpaired electron. Because of that unpaired electron, this NO, nitric oxide, dimerizes. It can be dimerizes. And one point I am writing here, dimeric form of NO is diamagnetic. NO odd electron becomes dimeric structure. So no odd electron in the dimeric structure and becomes paramagnetic, becomes diamagnetic. Next point. NO, it converted into NO plus. In NO, bond order 2.5 according to MOT. In bond order here is 3. Therefore, if NO converted into NO plus, bond order increases, means bond energy increases, means stability increases. Since bond order is increasing, more bond order, less is the bond length. So bond length decreases. Mainly I want this point. And more stable in NO plus. That's why in most of the complexes, not all, none, most of the complexes, NO exists as NO plus. Example, brown ring complex, Fe H2O 5 times NO plus 2 plus. One more example, sodium nitroprusside we are using for detecting sulfides, Na2 Fe Cn5 NO plus. And that means this NO, like ligand supplies 2 electrons, other ligands. In addition to that, it is supplying extra odd electron also. That's why also act as 3 electron donor. In some complexes, it donates its odd electron to metal also. That means it behaves like 3 electron donor. Like ligands, it donates 2 electrons. In addition to that, it can donate its odd electron and becomes 3 electron donor. P electron donor, observe here. Suppose I am writing here FeCO5. Now I am writing 2 NO molecules, 2 nitric acid molecules. Cr, CO taken 6 times. I am adding here, I am introducing 4 nitric oxide molecules. these two reactions supports NO act as 3 electron donor. See, in first example, in place of 3 carbon monoxide molecules, 2 NOs are substituted. Okay, so for balancing number of electrons, Nana, 3 carbon monoxide molecules means 3 into 2, 6 electrons satisfied by only 2 nitric oxide molecules. So 3 carbon monoxide electrons satisfied by 2 NO molecules means 6 electrons satisfied by 2 NO molecules. That means each NO function as 3 electron donor. In second example, 6 COs means 12 electrons of carbon monoxide satisfied by 4 NOs. 4 into 3 is 12. Therefore, 12 electrons of 6 carbon monoxide molecules satisfied by 4 into 3 electrons of NO molecules. So these two reactions are good examples of showing NO act as a 3 electron donor. Next one. N2O3, dinitrogen trioxide. In this N2O3, N2O3, nitrogen maximum form 4 bonds only. It won't form 5 bonds, Nana. It form only 4 bonds maximum. That too, the fourth bond formed by nitrogen K2 bond only. So, K2 bonded oxygen. Then, this oxygen carries 2 lone pairs. This oxygen 2 lone pairs. This nitrogen 1 lone pair. Whereas K2 bonded oxygen 3 lone pairs. We have double bond O. Bond O bond. Now we have K2 bonded oxygen also. Double bond O, 2 lone pairs. 2 single bond O's, 2 lone pairs. K2 bond O, 3 lone pairs. We have the different forms of oxygens. Third one rarely, Nana. Okay. First give importance to double bond O and 2 single bonds. If those two are not suitable for explaining bonding, then only please move to third case, K2 bond oxygen. We have one more structure for this N2O3. Double bond O, 2 lone pairs, single bond O, 2 lone pairs, 2 lone pairs, and 1 lone pair here. So in both structures, overall in one molecule we have 8 lone pairs of electrons. The second one is called symmetrical structure, and first one is called unsymmetrical structure. This N2O3 N2O3. Now I'm going to NO2 molecule. Nitrogen 5 electrons, 2 into 6, 12 electrons, total 17 electrons. 17 electrons means 8 pairs plus 1 extra electron. That's why this is also odd electron molecule. tetroxide, it has a characteristic color, red-brown gas, reddish-brown colored gas. This NO2 is a bent molecule. With a bond angle of 134 degrees. Please remember this value, very important for NO2. Experimental value 134 degrees. NO2, nitrogen, double bond O, Day2 bond O. So, double bond O, 2 lone pairs, Day2 bond O, 3 lone pairs. Total how many electrons are over? 2, 4, 6, 8, 10, 16, and 1 odd electron near nitrogen. In one of the resonating structure, that electron we can write in bonding also, like NO. It is called 3 electron bond. So NO2 contains 3 electron bond. And because of odd electron, like NO, this also dimerizes. Okay. This NO2 dimerizes like NO. But dimeric form is like NO is diamagnetic, no odd electron. The dimeric form, very important compound, Nana, is N2O4, dinitrogen tetroxide. I want to discuss a few points about this N2O4, dinitrogen tetroxide. This N2O4 contains NN linkage, maximum 4 bonds. So Day2 bonded oxygen, double bond O, 2 lone pairs, day 2 bond oxygen, 3 lone pairs. Okay, this is structure. Important point is liquid form of N2O4, because NO2 is gas, no? That gas converted into dimeric structure. In the dimeric structure of N2O4, we have both liquid as well as solid form. On cooling NO2 gas, it is becoming N2O4, liquid or solid. Mainly liquid form plays important role. This liquid N2O4 act as non-aqueous solvent. Non-aqueous solvent means it ionizes like this. In liquid form, it ionizes as NO plus and NO3 minus. NO plus and NO3 minus ionization. For this, what is the proof of this ionic form of N2O4? This is called as self-ionization. N2O4 self-ionizes to NO plus and NO3 minus. Now, based on this, observe here. NOCl, I am writing one compound. Plus NH4NO3 gives rise to NH4Cl plus N2O4. One reaction I mentioned like this. So here we have NOCl, here we have ammonium nitrate. So I am highlighting NO here, I am highlighting NO3 here. My NH4NO3 means NH4 plus NO3 minus. Here NO plus Cl minus. Combination of these two. Combination of these two. NH4Cl plus N2O4. So this is one proof for N2O4, which exists as NO plus and NO3 minus in solution state. One more example I am giving. Right. Zinc chloride plus N2O4 gives rise to NOCl plus zinc nitrate. This is the reaction they observed. Zn plus 2 Cl minus. Here we have NO plus NO3 minus. Combination of these two and combination of these two. So N2O4 contains NO plus and NO3 minus ions. For this, these two reactions best examples. To show N2O4 contains NO plus and NO3 minus. And one more important principle here, once again, I am writing that top example, first example, that is NOCl plus NH4NO3 gives rise to NH4Cl plus N2O4. NOCl I am comparing with HCl. NH4NO3 I am comparing with NH4OH. Gives rise to NH4Cl plus H2O. My second reaction is aqueous solution. first reaction is non-aqueous solution. There is no water, no. So first one is non-aqueous reaction and second one is aqueous reaction. So HCl and NOCl. Here H plus, here NO plus. In second reaction OH minus, NO3 minus. That means this NOCl they consider as acid and NH4NO3 considered as base and ammonium chloride salt. N2O4 now solvent I am writing, not water. And now they defined acid and base in N2O4 solvent also. Generally, substance which gives H plus is acid, substance which gives OH minus is base. In any solvent, no, in the aqueous solution. In water only those definitions are valid. In aqueous solution, substance which gives H plus is acid. In aqueous solution, substance which gives OH minus is called base. Now, we are giving new definitions for acids and bases in N2O4 solvent, not in H2O. So in N2O4 solvent, substance which gives NO plus is called as acid. In N2O4 solvent, the substance which gives NO3 minus is called as base. అంటే ఇక్కడ చూడండి N2O4, this is important conclusion. N2O4 sulfinases to NO plus, NO3 minus. This species considered as acid. This species considered as base. Therefore, in N2O4, substances containing NO plus or acids substances containing NO3 minus are bases. These definitions are valid only in N2O4 solvent. So new definitions for acids and bases in N2O4 solvent. And this is important in the oxides of nitrogen. Regarding N2O4, liquid form of N2O4 undergo sulfination and act as non-aqueous solvent and involves a special type of acid-base reaction. అంటే ఈ రియాక్షన్ ఇప్పుడు NOCl plus NH4NO3 gives rise to NH4Cl plus N2O4 is also called neutralization reaction. Neutralization reaction in N2O4, a special neutralization reaction. Therefore, NOCl plus NH4NO3 gives rise to NH4Cl plus N2O4. One type of neutralization reaction. Neutralization reaction in N2O4. Next, last species, that is N2O5. This N2O5 contains NO-N linkage, nitrogen, oxygen nitrogen linkage in gas phase in gaseous state. So nitrogen, oxygen, nitrogen, double bond O, double bond O, day 2 bonded O, day 2 bonded O. So number of lone pairs practice చేసుకున్నాను in all these oxides of nitrogen. Single bond O, 2 lone pairs, double bond O, 2 lone pairs, day 2 bonded O, 3 lone pairs. And we also, one important point we have, that is solid form of N2O5, not gaseous form, Nana. Solid form of N2O5, it shows some ionic nature. But this is structure in gas phase. In solid state, it shows some ionic character and exists as NO2 plus, NO3 minus, called as nitronium nitrate. Nitronium nitrate is the one more name for solid form of N2O5. So N2O5 ionizes as NO2 plus and NO3 minus. For this, any proof is there? Yes. Like N2O4, to prove this N2O5 exists as NO2 plus and NO3 minus. One example I am writing now. 1 minute. Let us take N2O5. Now I am adding sodium chloride. Okay, ionic. Sodium chloride is ionic. So N2O5 in solid structure is NO2 plus, NO3 minus. Then the products are my Na plus Cl minus, Na, NO3 plus NO2Cl, not NO, NO2Cl. NO plus is nitrosyl, NO2 plus is nitrile chloride, this one. NOCl is nitrosyl chloride. One more we have N2O5 with sodium. Okay, so N2O5, NO2 plus, NO3 minus, sodium loses electron, electropositive metal supplies electrons very easily. This electron is applied to NO2 plus. It is electron deficient. If NO2 plus gains electron, that NO2 plus becomes NO2 plus, Na becomes Na plus, and combination of these two gives NaNO3. So these two reactions supports the ionic form of N2O5 in solid state as NO2 plus and NO3 minus. Overall, in these oxides of nitrogen, these two are very important points, N2O4 and N2O5. Liquid form of N2O4 exists as NO plus, NO3 minus. Solid form of N2O5 exists as NO2 plus and NO3 minus. That point I am like conclusion point regarding oxides of nitrogen. Liquid N2O4, NO plus, NO3 minus. Solid N2O5, NO2 plus, NO3 minus. So these are the some important points related to oxides of nitrogen. Okay, Nana. And tomorrow, oxides of phosphorus, then oxides of sulfur, then oxides of chlorine. Then we are going to oxyacids. Tomorrow we'll continue now. Right. Thank you.
Yes, sir.
Hello?
Yes.
Great. Thank you, Nana.
Thank you, sir.
Thank